right
well, this is
now.
going to be weird, and it's going to be about a different.
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Ruliad. I don't think it rules them all. And it might
Yeah,
be just
instead
hyper Rulial Turtles all the way down.
yes, it's on the back of an infinite number of hyperrural turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. I'm joined by Brad Voorhees from the Sonic Gravity podcast. He is also a fellow honorable mention and perhaps also a fellow madman, if you would here. And I literally just got done finishing up the complete thing because I think it was pushing like 2 hours, and I'm like, there's a lot of stuff. And
I'm really sorry about that.
No, dude, because you initially, I feel like the thing that captured my attention, which may have maybe turned some other folks off, is you start off the whole thing. It's like imaginary numbers. This accounts for our unexplained mass, and that's a fact. I'm like, that is a very bold statement, sir. But I'm like, recent events and stuff and things kind of has my mind going in that direction. So I'm like, let me listen to this person, because just my base intuition is any sufficiently crazy idea is indistinguishable from madness, I claim. And it sounds like a whole bunch of different bad stuff and things. But Brad, why don't you tell the good folks who you are and just kind of like what got you going and interested in this direction?
Oh yeah, well, Brad, I'm a dad. I'm a veteran. I'm an engineer by education, lawyer, and I work for the federal government. And in my spare time, I started podcasting, and I had a mentor, or a mentee. I'm sorry, this little program, and yeah, I'm neurodivergent, right? So I'm bipolar, autistic, and technically I've ASPD, which is antisocial personality disorder, and so I'm sort of what you call neurodivergent, and we were talking, and my mentee and I mean, you just hit it off, and he's like, you should podcast, like seriously, and we profoundly affected each other's lives, just from our discussions and stuff like that. So I started podcasting about what was going on inside my brain, and then UFOs happened. The Pentagon, the Navy said UFOs are real. This was maybe 2 years ago, the beginning of 2021.
There were unexplained aerial phenomena. I think the UAP is the moniker we're going with. Like right now, it's like,
sure, yeah. They call it, we'll call it whatever they want to.
Yeah.
And it was, I was just looked at him. I was like, okay, I got to figure that out, because once I don't understand something that I know that I want to know, it's kind of like a splinter in my brain. I just can't stop thinking about it. My brain starts cycling, and it took me a couple months to figure it out. And like after 6 months or so, I sort of fell into this theory of everything. I didn't even know what a theory of everything was, but all of the stuff that I had to learn, because I learned quantum physics on PBS Spacetime with Dr. Matt O'Dowd. I was just watching PBS Spacetime.
Excellent channel.
Yeah. I mean, it was really, it was really very simple. I looked at them. They were zipping around. I'm like, dude, those are massless. They have to be massless. Because I saw one. I mean, I just assumed. I said, well, okay, here's the thing. I can see it. If you got me. If it's a fake and it's not for real, then okay, they fooled me. But I'm just gonna assume it's what I'm looking at. The Navy said is legit. It's a UFO.
If what we are seeing and the numbers and the stuff and things that they've thrown at us, let us assume that's correct. How the heck could one do that?
I mean, I'm not gonna, people could go, oh, they're hoax. And like, some people probably make fake ones too. Like, some clown shoes are gonna do stupid shit like that, waste everybody's time. It's gonna happen. But there's stuff that like I look at and I go, now I look at, and there are predictions that if the things that I think about them are right, there are predictions that have to be true. And so those are actually the things that I look for to see if I think, oh, well, that's maybe right, or no, it's not, or whatever. But I saw him take off like instantaneous velocity. I'm like, well, okay, it's got to be massless, right? Because if that thing has mass, just the inertia of its own acceleration would pancake it. It doesn't matter if it's a drone, whatever, it would just crush itself with that kind of acceleration. So it has to be massless. And so then I was like, I got into quantum physics and I was like, okay, I need to find out what causes mass because I got to get rid of it. I got to break it. And so I was watching PBS Spacetime and it turns out there's something called the Higgs field. And the Higgs field is like, you can imagine like space, right? Like just everywhere. The Higgs field sort of like, imagine like sort of air, like in the room you're in. It's everywhere, even in a vacuum. And it's got a non-zero value, which means even in a vacuum and empty space, there's a quantum field that's just kind of buzzing that has a value that's non-zero. And it turns out that's the Higgs field. And I think it's consensus that that is what gives matter mass. It's not like the Higgs boson is heavy. It doesn't give matter mass that way, but it's essentially the field moving through the field. It takes force to move through, and that's what gives you essentially weight. So, so how do you get rid of that? So I looked up, I was watching more Space-Time, and it turns out that the Higgs field is hanging up the electron. Now, electrons spin, I don't want to get too far into the weeds yet, we can, but there's essentially a left-handed chiral electron, which is sort of like a positron, which is the reverse, antimatter kind of particle.
Our realm persistence has kind of like a left-handed bias, if you would. There.
Yep.
Just to push back with love and respect,
Sure.
I believe at least the Higgs, at least the particle, is actually about 133 proton masses, at least according to Wolfram Alpha here. I'm not sure if that's what you were saying. Basically, it sounds like, and correct me if I'm wrong, it sounds like your conjecture is essentially the vacuum, which apparently is there no true vacuum because there's actually something rather than nothing there. We've seen quantum fluctuations there. It's just colloquially we say vacuum, people think that there's nothing, but there's actually something. So it sounds like your conjecture is basically the Higgs field. It permeates throughout everything here. Is what
that's not my conjecture. That's consensus.
Okay.
Yeah. So like that part is not, I think what I've said right to this point.
Okay.
Yeah, what I've said to this point is absolutely not controversial at all. This is total consensus. It's like the Higgs field's there. It's throughout all of space. The vacuum expectation value is 246 gigaelectron volts or something like that. So that's not me. I'm just taking their word for it. I'm just taking Peter Higgs and CERN's word for it and all that. And,
not to get up. I caught up there. It's just I heard some things that I wasn't sure, so I just wanted to just put that there. But no, continue how you kind of got through this because I know the number negative 246 comes up.
Oh yeah. So here's the thing, and so it's 246 gigaelectron volts is the vacuum expectation value of the field, and so I'm thinking to myself, well, like, okay, I need to cancel that, right? I need to, if I want anti-gravity, that has to go to zero, right? That's just, if you want anti-gravity, if the Higgs is given matter mass, and if anti-gravity means you're massless, right? Then that means you got to somehow drop that vacuum expectation, that value, that non-zero value, you have to drop it to zero, right? I mean, that's not controversial. That's totally logical. Like, I don't think anybody can argue with that. If you want anti-gravity, that field's got to be zero. That field is,
all I know is at least if I go into Wolfram Alpha, if I type 200 and 46 electron volts and a gigaelectron volts, and then I minus 246, I'm gonna get zero, right?
Yeah. I mean,
that's logical. That seems like a good way how one would go about it if one's trying to solve for how do we get rid of gravity.
Yeah, I mean, like this is how I did it. Like, so this is not like it's really not rocket science. Like I think anybody can do it, and I'll tell you how to do it. I'll tell you how I've been trying to do it. And so, and I've got my rig to drop about 200, about 2.5 pounds. Like, and I have it on video, but
I just find it interesting here. I just type in not negative, but 246 gigaelectron volts.
Sure.
This would be about twice the mass energy of the Higgs boson particle. I find
And
that
hey,
interesting.
remember that twice. Remember that, because I'll
Okay.
tell you why it's 2. The G
I
factor's
think
2.
I might know why.
Yeah, you
Continue,
know,
sir.
if you've watched it, you know the holographic universe. Yeah, you got it. So,
Continue,
but
sir.
yeah, so the what you got to do is you got to drop that value to 0. And so what I was looking for as I was doing, farming through a PBS spacetime is I'm like, well, what's hanging on to the Higgs field? How do I get a hold of the Higgs field? Because if you can't grab it and and mess with it, like then you're kind of stuck, right? And well, it turns out, and I can't remember which episodes, in several of my episodes, but the left-handed chiral electron is, and this is Dr. Matt O'Dowd on PBS Spacetime saying this, is constantly getting hung up by the Higgs field. The Higgs field is pulling on the left-handed electron, and it does it as the left-handed electron trades what they call the weak hypercharge back and forth. So, and what I think is happening when, just as an aside, is you have your hologram, right? Your holographic universe, U1 symmetry as the left-handed electron. And so, I think the reason there's 2 is because, an oscillation in U1 symmetry is going to punch through as matter off the hologram. It's dark matter. Bam, it's coming through as antimatter. Now it's because in contact with the hologram, when it's matter and antimatter, that is when we can interact with the particle, is because our consciousness is sitting on the hologram, and that's where it's getting its information from. And when it swings off the hologram is when it's dark matter. It's matter swinging off the hologram is dark matter. Remember, it's matter as it's hitting. Now it's matter. Now it's dark matter. Now it's antimatter when it's here in the whoop. Okay. When it crosses, it's antimatter. Now it's dark matter again. So that's your U1. Now the leash that holds that particle in that oscillation is the Higgs field. That's what I think is the Higgs field. Now that would be that's what you'd call U2 symmetry. And that's the tension in that leash. Now that is not consensus, right? Everybody else thinks that that's like, 3-dimensional, strong nuclear force, weak nuclear force. That's what U2 is. I think the tension at leash is the Higgs field. I think if I could get, like real physicists to be like, hey, dude, just call that gravity, the tension, the Higgs field. Because if that U2 symmetry, that tension in that leash, if that becomes gravity, now you have the plane of the hologram, which is space-time, the surface of space-time, right? And so as this matter oscillates, the more matter in that plane that oscillates, right, you're going to deflect space-time, right? Because that leash is holding on space-time. So now it's spinning around. Now the more mass you have spinning around, now it's bending space-time.
And that form of inertia.
That's GR. Because GR is the deflection of space-time from energy, from the gravity arising from the presence of energy in space. And so right there, if that is, valid, that is the unification of GR. And it really is. That's the unification of quantum mechanics and general relativity. So is that energy zipping through a hologram is going to deflect space-time if gravity is that U2 symmetry, that leash that's tying it. And now it's crazy is that, like, say, I'm trying to like do this so you can see it. So like you've got your hologram right here, right? Space, if the universe is a hologram, then your matter, it's dark matter off the hologram. It's antimatter when it comes back around and it's off the hologram and it's dark matter. And then it's matter when it hits at the 12 o'clock spot. Now, so if you watch Kurt's episode with Dr. Ashkakar, because he says loop quantum gravity is a particle, and then it's a relationship, and then it's a self-dual particle of opposite helicity, which is antimatter. Guess what? Going back and then coming back off. And so that's loop quantum gravity. It's describing loop quantum. That's an ontology that is an exact reflection. Yeah, well, it's an oscillation, right? It's energy. And so, and here's the crazy part. So say you assume a 4-unit diameter, right? So now you got 12 and a half, essentially 12 and a half perimeter, right? Pi times diameter, 12 and a half this way. Well, if one is here as matter and then one's here as antimatter, that's 2, where it's in contact with the hologram, where it's real. There's 2 to 10.55 of dark matter off each side. And 2 to 10.55 or 1 to 5.25 is the exact measured ratio of dark matter to matter in the universe, and that's a fact.
Really?
Yeah, it's a fact, dude. I'm not making that up.
What was that again?
Okay, so 1 to 5.25.
One raised
is the
to
1
colon.
I'm sorry. Look, my daughter painted my fingernail. When you're
I'm gonna judge that. I've had girls put stuff and things on me.
Yeah, I just don't want that to distract you from the unification of general relativity and quantum mechanics. So, yeah, so the 1 to 5.25 is the exact measured ratio of matter to dark matter in the universe, and that's a fact. And I'm not making that up. It just is what it is, and it all fits. It fits perfectly, and that's what you see. Like if you think about, and I didn't make up the holographic principle. That's not me. That's Gerard de Hoof, Leonard Susskind, Jacob Bekenstein, probably. There's all these like brilliant physicists that sort all that out.
Oh, it's 1. I type in what you said, 1 colon 5.25. Okay. That chart. Oh, that seems to match up pretty nice with was it dark matter and matter? What was it?
Yeah, I mean that's
there's like about 5 times the ratio. Yeah. Cool. Continue.
Yeah, and so now too, there's also something called the G factor, which people don't understand, or people don't know why. So there's Einstein and de Haas, right? They had this brilliant experiment. They're trying to come up with what the electromagnetic dipole moment is of stuff, and like essentially, what's the momentum, the rotational momentum of like an atom. And so what they did was they took a big block of iron and hung it in a magnetic field, and then it's kind of like everything was all jumbled up, but the momentum needs to be conserved. So when the field is placed, it straightens out all these atoms, so they're spinning around the same way, and then the block of iron will rotate reverse because that momentum, the initial momentum, has to be conserved. So if everything flips over and is going this way, an opposing momentum has to happen to turn it. And essentially they did the math, and they're like, it's always spinning twice with twice the energy than our theoretical calculations come up with.
Because it was supposed to be 1, wasn't it? Something like that.
Yeah,
it's supposed to be 1,
but it's always twice. And so they called that the G factor, and it's a cheat, and they don't know why that it's always 2. And so, but the reason it's always 2 is because if you're living in a holographic universe and there's an impulse here, so there's one pushing this way, but then when it swings back around, there's another one this way. Well, that's like 2, right? And so the momentum is actually double because we're in a holographic universe. And so it also explains the G factor. And there was a experiment by the Fermi Lab, which is a bunch of smart physicists in Chicago, and they did an experiment, and they're like, oh, look, the G factor for the muon, right, which is essentially kind of a big fat electron. And we can talk about that. Yeah, I don't think there's 3 generations matter at all. If you've like seen the TOE that it's just a slow electron. But we'll talk about. We can talk about that.
You're saying it's under a different energy because of it's either acceleration or its rate of speed or something like that.
Yeah.
Okay.
Yeah.
No, I remember you saying that.
Yeah. Yeah. So because everything is the same except for mass, and you know what? Even the particles in the standard model, there's no like fixed mass for anything. Even though they put, here's like the expectation. None of those numbers are etched in stone, and the reason is because and I'll try to be careful when I say the reason is and this and that, because when I'm talking about the sonic gravity theory of everything, just imagine I'm saying, well, under my theory of everything, you know what I mean?
You're conjecturing. It's like, hey, this is what my intuition is leading me towards. This is what I expect it to be. Here's my logic. I heard you.
Yeah.
And again,
I would say it's more than a conjecture. It's definitely more than a conjecture.
You assembled. Yeah. One of the things that I like is you assembled a whole bunch of different pieces. You're like, I got this itch in my brain. I want to figure out why. And it's like, God bless the internet. It's like, we now have access to exponentially the amount of information from the libraries of Alexandria, literally at our fingertips, being able to access articles, videos, this, that, and the other thing. Because I spent like
But
an entire
in the
summer listening to Sean
brains
Carroll's. Yeah.
and the thought processes of like brilliant people.
Mm.
It's more than just books too. I mean, because like when it comes to, the things I'm talking, most of these things that I'm talking about are not anything that I figured out. It's stuff that I'm like, okay, that makes sense. What you're saying is like legit in science. Like that makes sense. I'm putting that down and I put that in my puzzle, but when something conflicts, that's when I go back and I'm like, okay, this conflicts with that. So why? And that's when I like start to noodle, and it's the things that aren't consensus in science that I put in the sonic gravity theory of everything are the things that need to happen so that the things that I know we know. We talked about like know what you know and what you don't know, and the boundaries of that puzzle piece of what you know. And I find that most of the stuff that I'm saying, no, that's not right, that's not how it works, is when there's a measurement, and it's not the measurement that we're arguing with, it's the interpretation of the measurement. And so, when, say there's like a particle accelerated and it smashes another atom, and boom, all of a sudden, there's a certain amount of energy that goes into this collision. And well, now all of a sudden there's orders of magnitude more massive particles in the aftermath of this collision. This is a fact. Like this is a total fact. And so what the consensus physicists think is that you shoot like, maybe protons or whatever it is in the causes collision.
So basically, sorry to cut you off there.
No, yeah, go ahead.
But just in my mind, you're saying this and like straight up and what I love about like a lot of stuff that's out there, it's like, and people like Matt O'Dowd, Professor O'Dowd from PBS Space Time do extremely well.
Oh yeah, he's awesome.
They present it in a way that both professional and layperson, the average Sally, Dick, or Jane, can at least be entertained and just be like, oh, this is pretty cool. And it sounds like what you're saying there is like in some of these particle acceleration things, it's like, all right, we're smashing these things together, and then we end up detecting a particle that somehow has more mass than what we threw at it.
Yeah,
and that's
every time,
weird,
not just sometimes,
awesome.
Every time. There's
Top
thousands more
than
mass.
And here's why. Jogging.
It's like, so like when all this stuff comes in, you've got these super accelerated particles, and like, particles come the other way, they hit and they, fracture, and the mass of those particles could be hundreds or even thousands of times more than what went in. And here's why, is because conservation of mass energy on the hologram. So everything's going rocketing at, near light speed. And then all of a sudden, there's an impact, and now it's all not going light speed anymore, right? Because, the electron that was orbiting, a proton or some kind of positive ion. Well, when that ion just blows into quarks, right? Now the electron's not orbiting anything, right? So it's not zipping around at light speed. It's not orbiting anything. And so in order for it to maintain the same energy, the same way that when they put the block of iron, it had to start spinning to maintain that momentum,
a different state.
Yeah, it has to, it more mass that was in a dark matter state, I think, comes onto the hologram to compensate for the loss of momentum energy, loss of velocity. And so all of a sudden it gets big and fat, because it was like, say it was like at 100 energy, and it was maybe one mass, but it was spinning super fast at 100, units of velocity or whatever. Well, all of a sudden the proton that it was orbiting around just vaporizes or disappears or shoots. So now it's not orbiting anything, right? It wasn't going anywhere. It's not orbiting anything, but that little electron has to be at the same energy that it was before, because that would, if it doesn't, then that would violate the conservation of mass energy. So the reserve mass that's oscillating on the hologram is when it slows down and almost stops. Well, some of that mass just it just appears on the hologram. It essentially transmutes, I think, from a dark matter state into an observable mass on the hologram until the electron gets picked up by another ion, starts to accelerate, and then when it starts to accelerate, the mass will drop, and more of it will go into a dark matter state. And we call that decay. And so the consensus, then okay, so here is where, and I don't want to be disrespectful, but here's what the consensus view is. Collision happens, magic particles come out of nowhere, like muons, right, that are heavy, and then they decay, they shoot out other magic particles. Now they're supposed to be elementary particles, but then they shoot out other, where do those other elementary particles come from? I don't know, but it's not like, a bunch of neutrinos makes up a muon, but all of a sudden muon's shooting out neutrinos, and then it becomes back to an electron. So
like matter, antimatter, particle production.
Well, no. What it says, it's like it allegedly emits a bunch of neutrinos, and the mass of those neutrinos, right, like it reduces its mass. So the electron, who knows where it went? All of a sudden, boom! It's a muon. It's a magic muon, 200 times heavier than an electron, and then it decays by shooting out neutrinos, and now it's an electron again.
Now it's electron. Yeah.
Nah, I don't see. I just don't buy it. I just think conservation of mass energy. There's a certain energy it's got to stay at. It's off the hologram. It's oscillating. Most of its matter is off the hologram because it's going around a proton, like almost at light speed, and then the proton explodes in some kind of collision, and then the electron kind of embiggens because it needs to maintain the same energy, and E equals mc squared, right? So it would gain mass if it lost velocity really rapidly, because if it lost like 99, you would just go, well, 99 divided by c squared, that's how much mass it would gain, right? And so that it gains that mass, but then when it accelerates, when it gets picked up by another ion, starts to accelerate, then it decays. So, but anyway, this is what we were talking about. We were talking about how do spaceships fly, but so anyway, yeah. So that's like sort of the sonic gravity theory of everything, and that's where it departs from. One way that it significantly departs from the consensus view of the standard model particle physics is because I think it's just an electron, but it just embiggens on the hologram when it loses velocity, to maintain a constant mass energy, which is required by the law of conservation of mass energy.
So what sounds like you're conjecturing is, it sounds like basically a lot of consensus based upon what you said is like, all right, you have this, it's emitting neutrinos to help maintain that conservation of energy. You're saying that it's different in that almost, it sounds more like, I believe it's an ADS CFT, the anti-de Sitter space conformal field theory, in that like you have like a boundary here, you have a boundary here, and then basically the hologram per se is basically kind of like the bulk in between, something like that.
Well, okay, so
I realize ADS CFT is probably
no. That's like, I mean, so the holographic principle, right, is that if we believe we live on a hologram, right? Yeah. Now, so the bulk is different, like where my understanding is. So if you believe that we're in a hologram, right? So then what that means is essentially, you can think of it like sort of like VR, right? So, and this is so silly. I love my daughter though, so she says, "I want to paint your nails, Daddy." The answer is, "Okay, come paint them."
Oh, this is so fantastic! Yeah. I love it. It enhances it.
So like if you're on a hologram, right? So what it would be like the resolution of the hologram is the depth of your 3D space. It's not 3D, but the resolution is 3D. The same way that the further things are away, the smaller they get. And so the bulk would be when you look at all the resolutions all at the same time. That's when it looks like the bulk. So when you look out into the sky, when you look and you see the cosmic microwave background, what you're seeing, the cosmic microwave background, is sort of like, or at least the highest, or the lowest sort of resolution that we can perceive, right? But you're seeing all those resolutions all at the same time. That's the bulk, right? And so it looks 3D, it looks deep, and that's sort of what the bulk is. It's like, or you could think of it like I talk about it like
where gravity kind of like primarily takes effect, because it's like you've got this, or at least that's what I think Jonathan Garrod
Well,
kind of.
well, gravity is
explained
short distance acting, right? And that's because it only needs to go through the hologram. So gravity, when they say, oh, gravity is so short acting, yeah, obviously it's short acting because it's on the hologram. It doesn't. That's the bulk. Like that's just the resolution. Gravity can go all the way through the universe, and it doesn't have to be long acting because in reality it's a hologram, which is practically one dimensional, and it's just needs to essentially hold everything to the surface of the hologram. So because it's weird because like scientists, they really believe that we're in a 3D universe, and if we are in a 3D universe, none of what I'm saying is going to count. It's not going to make any sense. Essentially, for me, for my theory of everything and all that kind of stuff, we have to live on a hologram. But when you look at quantum entanglement, right, it totally explains quantum entanglement because you draw a hologram, right? So you got your particle, it's oscillating, it's matter, it's dark matter, it's antimatter, it's dark matter off the hologram, it's matter, it's dark, and then it's antimatter. Well, now your quantum entanglement, right? And any physicist will tell you, quantum entangled particles, any quantum state, right? Well, it's going to be opposite, right? So if it's going like this, you got a direction this way, you got a direction that way. If this is a positive charge, this is going to be a negative charge. If it's left-handed chiral this way, then it's going to be right-handed chiral this way. So that's why it's matter and antimatter. But now when you hammer that particle with a laser and you send that antiparticle away, now your quantum entanglement, I mean, it's just looking at both parts of the contact with the hologram at the same time. And so when you hammer that particle with a laser, you excite it, you're really just expanding that orbit. And so you're stretching the particle out in space. And so the whole discussion,
kind of forming it.
Yeah, well, you're essentially you're putting energy into it, and you're exciting the distance. You're essentially, they were hammering those particles with a laser. They were splitting those quantumly entangled particles apart. And why that was relevant to them was because they were saying, well, now we can observe this particle. And then remember, because they're opposite all the time, right? And so if you look at this particle, you could look at this particle, measure both of them, and they're saying this, there's non-locality, or this locality influence, information traveling at the speed of light. They were knowing what this particle was before light could get to that particle to tell it what its quantum state was. And so what they're saying is like when you collapse. Okay.
Oh, sure. No. Sorry. To kind of like just like it's like steel man a little bit, kind of like what you were saying there, because a lot of folks are like the speed of light is the maximum like speed in the universe, and it's like, okay, it generally was a Planck length divided by Planck time. Okay, I can understand that. That makes sense to me. But then again, I go into Wolfram Alpha, and I had remembered this from before. I'm like, the lower limit on the speed of quantum information, 1.6 times 10 to the 13 meters per second. And I'm like, wait, the speed of light's like 2.98 times 10 to the 8 meters per second. I'm like, that's like 5 orders of magnitude larger than the speed of light, and that's the lower limit on it. I
don't know.
That's interesting.
I don't know what that is. I mean, my understanding though of the quantum entanglement discussion, as far as the speed of information, and the reason Einstein didn't like that spooky action at a distance was because, they were saying that there's sort of instantaneous communication, and so Einstein's like, no, when you collapse the wave function here, because they're in a superposition of states, and an observer has to observe what that state is in order for it to like achieve a state, which means this one is undefined, is fundamentally undefined, and this one's fundamentally, when an observer views it, it's defined. But then over here on the antiparticle, then this one's the opposite. But one of the principles of quantum mechanics is that you have to, the observer has to collapse the wave has to collapse the wave function to determine, cancel out all the probabilities and isolate what that value is. And then, that one's the opposite. And so, but what they did was they hammered this with energy. They hammered this particle with energy and split the distance out far enough to where they knew that when they collapsed this wave function and were measuring that one, they were measuring this one after this one was collapsed and knew what this one was before the speed of light could inform that one what it should be. And so what they're saying is that information doesn't travel, or, you know, and so yeah, and it was sort of disproving what Einstein said. He said, no, it shouldn't, you shouldn't, that shouldn't know. But here's the thing, is the reason everybody's right is because it's the same particle. And so when you collapse this one, do you see what I'm saying? You know, the particle, it's an orbit, right, going through a hologram. And so you have the particle, and
basically non-locality explains it.
I mean,
that's what I'm hearing.
You already know it's the same particle. It's the reason it's not a quantumly, they're not separate particles. It has to be, and then everybody's right? If
you're
you realize
saying the action that we take is creating it, is creating,
you're collapsing, the particle, but you're automatically, it's the same particle. So when you're observing this one, you're still affecting this one because it's the same energy, right? It's just, you know, it's just going through the hologram. It's going through the hologram in two spots, and you're just looking at one of them.
Ooh, see, that would be very, very interesting. Now, Professor Sean Carroll may take up a bit of issue with that. I don't know. I can't speak for the man, but all I know is let's go to actually
they know a lot more than me. They know
let's go to Jack's question here. Basically, like, what can we actually get out of this? And I'm sorry, we went on a complete tangent there, but as far as I understand it, you've gotten the ability to shave off measured mass per se from things. Basically, how could we get some of those UAPs, triangles, or Tic Tacs to actually help improve humanity by whatever means? What's going on?
Well, let me tell you though, and I did a podcast on this one. The last episode I did is called The Real Prime Directive. And it's like, and I don't want to be disrespectful or anything, but it's like what they were doing. Like, do you realize they don't know this? They think these two particles are different, right? They think they're two different particles. So I get that they're not going to track this, but they're the same. And if they are the same particle, then what they just figured out with their sort of, and I was saying they were scientifically masturbating with the technology they need to teleport things. Like, that is Star Trek beaming. Because if this is a particle and you hammer this and you extend that antiparticle out, you catch that antiparticle in a field and then hammer the antiparticle with the same laser, I am certain if you oppose the direction of motion of that other particle, you'll reel that particle back in, and you just teleported. That is Star Trek beaming right there. If you hold that particle, you hammer it with a laser, it extends that antiparticle out to wherever you want to teleport to. Then you catch that particle in a field, hammer it with the same laser, and you reel this particle in.
You can communicate the information from the first.
No, you can teleport. You can translocate a particle in space. If we live in
conjecture. Okay, yeah.
If my theory of everything is true, we're on a hologram. This particle is going like this. If my impression, my belief that when they're hammering this particle with a laser and extending the antiparticle out in space, right? Say I wanted to teleport to here. So I extend this particle out in space here. If I catch that particle in a field, right, and then hammer this one, right, and so I'm essentially hitting it with energy in the opposite direction to slow it down, I will draw this other one in. And so if I can extend a particle out, catch it, and then hammer this one and draw it back, that's physical Star Trek beaming teleportation.
That sounds like something we could actually do an experiment on.
They did it. That's what I was saying, is that, dude, they got halfway to teleportation and then they just quit and said, look at the speed of information.
What are you talking about? Like the recent Nobel Prize for basically they proved entanglement?
Anton Zellinger.
That was my scientific thing of the year, just because I'm like,
amazing.
Yeah,
I mean, what he did is amazing. They're holding on to it, they're hammering that particle, they're extending it out in space, but then it's just like, then they're just like, see, look, but dude, no, come on, man.
You're saying that there's more. You're saying that.
And there's more, dude.
Oh, dude, I agree.
If my theory of everything's right, then that is Star Trek beaming, and that's a fact. is that you extend that
pretty
particle
sweet.
out, you catch it, and then hammer it with a laser, reel it back in. You just teleported that particle. Now, so surviving the trip, doing all of our particles, all that kind of, I mean, like that's a different thing, right? Because if you
Piece
just
of
shoot yourself with a
baryonic
laser,
matter.
yeah,
Human.
yeah. I mean,
So, yeah,
but
yeah.
I'm
We
anyway.
are made of
Bottom line
baryonic matter, so
that is
conceptually, I mean, yeah,
that's teleportation.
that's
I think they
fascinating.
figured out teleportation. They just don't realize it. They actually can do Star Trek beaming. If what I'm saying is right. If my theory of everything's right, then the 2022 Nobel is essentially the very first teleportation technology. Straight up Star Trek beaming, no lie. I mean, like not even an exaggeration. That's Star Trek.
I do it. If that is true, that would be absolutely fantastic. We just
Yeah.
need to get ourselves some replicators soon, so we can help take
Yeah.
care of.
Well, I mean,
maybe human
and
beings.
you
going
need a
hungry.
pad, right? You would need an electric field to catch those particles, right? Catch those particles, hold them right where you need them, and then hit them, with a laser.
correct.
The same way they hit the other one. Essentially, they're putting energy into it to extend, essentially expand the orbit in space. But then if you hit it with a laser and opposed it, essentially like, slowed it down, bumped it, I think you reel it back in.
That's pretty fascinating. So,
yeah.
Okay.
But think about it though. Now the crazy thing is that's Star Trek beaming. So is it an accident that that's a real thing?
I'm totally okay with it.
Is it an accident?
I have no idea. It sounds like it's working as intended. If that's true, I mean, it's.
Wait a minute. Okay, so now I'm going to blow your mind here.
Go on.
Anything in a universe that's infinite, anything that's possible, right, is inevitable, right? If it's possible in an infinite universe, it's inevitable.
Well, if you have enough time, you can. That's something I learned from Professor Sean Carroll. It's like if you happen to have infinity, that's a long time.
How old's the universe? Current
estimations are a little under 14 billion years.
14 billion, right?
Yeah.
How long since our planet got hit by an asteroid and reset? 65 million years, right? 65 million.
Yeah. If we go to there are astronomical things coincide, wipeout of dinosaurs and stuff.
Yeah. That's not an accident either. We'll talk about that in a minute.
Ooh.
But 65 million years, right?
Okay.
65 million years is how we're 14 billion. Okay, so there's something called the stationary action principle. And that means essentially path of least resistance. Like water always goes downhill. You know what I mean?
Principle least action.
Right. Except sometimes there's like little exceptions. So they call it the stationary action principle. But
okay. No. I'm open to that. Cool.
Totally. Yeah, no. It's good. And so here's the thing. There's two sort of schools of thought. Well, there's one school of thought. Everybody's like, oh, we're so lucky. It's so random that life's on the earth and da. No, it's not. There's something called the principle of stationary action. Any Earth-like planet, I would say, guaranteed always going to essentially evolve the same way that we did. Because the stationary action principle, we're not an accident. The universe has DNA. We have DNA. We're part of the universe. DNA happens. It always happens. Bottom line, I don't think humans are special. And because the universe is 14 billion years old and this exoplanet is only had life, kind of our sort of life growing on it for, 65 million years, we're not first. You know what that means? That means we are an exoplanet. That means we are the colony. We have to be. Because in any universe where humans can happen, it doesn't happen first here because we don't have 14. Somewhere there's an exoplanet or there's an Earth-like planet that's been undisturbed for 1 billion years. And we have 65
So you're
million.
saying there's a solution to Fermi's paradox is if the universe is wicked freaking big, statistically speaking, there be others out.
No, we are the exoplanet. We are the colony. We are not the first one. Ooh. We were planted here.
So
and now
so
when you start looking at
panspermia or intentional?
No, we're intentionally planted here. And now
very strong claim.
Star Trek I mean, no, it's if you agree, I don't think it's that. I think you have to get past our sort of human assumptions that 1, we're special, 2, we're first, 3, we're not part of the universe. Okay. Because we are part of we are the universe. Like I always say this, like, you're in a traffic jam, right? You're looking around and you think the universe is slowing you down, but to everybody else, you're the jam. Like we are part of the universe. Like we're not an accident. We're not special.
No, wait, we're all connected. You boil it down to energy and information. It's like, we're made computational equivalence right there, man. We are Star.
Yeah, I mean, you get a scratch on your face, right? What grows back? Face skin, right?
Yeah.
Face skin. You don't get toenails growing out of your face, right?
No, typically not. I want to see a doctor.
No.
Yeah.
Because you have DNA, right? Because your DNA is smart blocks, tells your cells what they need to be when they need to be there, right? So you're borrowing. I mean, essentially, you're the DNA. You are the universe's intentional, like, creation of energy. Like your DNA is not an accident. So because the stationary planet.
Coach was asking. Now, you saying that we were playing by patterns or potentially others? Because I have no idea what the truth is. I know some of those explanations. I mean, it would explain a lot. I did watch Prometheus. I did see how xenomorphs were born.
I don't know what that is.
And then again, I also am a fan of Lord of the Rings. And all I remember is a wise hobbit once said, the closer we are to danger, the further we are from harm. So,
Yeah, no, totally. No, I think we're planted by interstellar humans. I think we're an exoplanet colony. And
that would be a way to preserve humanity, per se.
Well, I mean, but look at it though. I mean, look at so I mean, it's funny because it's like, dude, like we are a colony. I think the more I think about it, it just doesn't seem that controversial. It doesn't seem.
You're saying that you're conjecturing that we are potentially. The conjecture is we are basically you are hypothesizing that it would explain a lot if human beings happen to be planted. Now, I have no idea whether that's true or not. It would explain a lot. I have no idea.
Well, there's a missing link, right? Look at the fossil record. Look at the fossil record 65 million years ago, right? There's all kinds of dinosaurs, crazy, all kinds of dinosaurs. And they all look like pretty much the same. 4 legs, long tails, long necks. They look almost all exactly the same. There's almost no mammals. And then, bam. Well, 250 million years ago, there was an asteroid about the size of Mount Everest that hit us right in the ass, right up the South Pole. And so there's a reason for that too, I think. But anyway, bottom line is it killed like 70% of the fish and like only 30% didn't kill all the dinosaurs. And so they threw another asteroid 65 million years ago that wiped out most of the dinosaurs.
Whoa. It's like intergalactic or maybe
no, it's just terraforming. It's
terrorism.
It's terraforming. It's not. It's like, well, I mean, think about it. You're an interstellar human species, right? You roll up on these 2 perfect exoplanets. And you're like, and I think they fucked up on Mars and just fucking hammered it because anyway, we can talk about that later. But
I've heard stories about that. But
I don't know. I mean, I'm just guessing. I'm just guessing because Olympus Mons, they know there was water all over Mars. Olympus Mons is a huge.
I've heard specific things about radioactive measurements that didn't necessarily make sense.
I don't know about any of that. I don't know about it. What I do know is that
I want to. If possible, could we get back to maybe like some of the actual like you're working through this here? Because as this is fun, I love the science, dude, and I love when you were drawing that circle and everything, and you were kind of explaining that out. Could we get to that? Because I feel like we need a whole other show for that. I feel like that's more of like an ontological thing, if you don't mind.
Well, I mean, the ontology, that's the only way that I can see things is like the ontology just. Essentially the Rosetta Stone, that there has to be a hologram. That's where we get our information from. Anything that's off the hologram, we can't perceive.
Can't detect it.
yeah, and that's why it's dark matter, right? Because we can't interact. So it's like weakly interacting, right?
Can,
And so
can we hop on that? Because that
except-
was the first. Sorry, go on.
yeah, no, and so except for if we agree, if we say, okay, U2 is a tension in this leash, which is gravity, leashing it to the surface of space-time, so we can see the dent in space-time, right? Because we're on the hologram. That's what Einstein made general relativity all about. And if we agree that, you know, this U2 is the tension in the Higgs field is you know, the gravity essentially, which is deflecting space-time. So here's the hologram, and then here's the U1 orbit, and U2 is the tension that holds this you know, this particle to the surface of space-time. That's the Higgs string. That's the tension in the Higgs string. And it's that tension in the Higgs string that deflects space-time, right? So the more mass you have, let's say over here. So the more mass you have, like the more energy you have, you know, oscillating on the hologram, right? The more that tension is going to kind of deflect the surface. And so now that's your energy, that's your mass deflecting space-time. That's GR. So there's a geometric like unity. That that's unification.
Now
that's unification
it almost
of GR
sounds like space is flowing in the way you're describing it.
Oh yeah. Yeah. Well,
okay.
Yes, that's true. That's a really interesting intuition that you picked that up. Because so here's the thing. The reason that the universe is expanding is because space-time is blowing through the hologram. And when something blows through the hologram, that's what changes the hologram, which is what we notice as the passage of time. And we know that neutrinos are blowing through, zillions and zillions of neutrinos are blowing through us all the time. But if we're stuck to the surface of this black hole and time is passing, well, if we're stuck to the surface of the black hole, we ain't going anywhere. We're sitting there on the black hole.
Step one. Let's take a step back because
wait, just I was about ready to answer.
Oh no, okay, go on.
Because it's not space, it's space-time, right? And we know time is passing us, but if we're stuck to the surface of the black hole, then that means space-time is blowing through us. Because it's not time moving through us, it's space-time moving through us. Which means if time is passing for us, that means, and we're on the surface of this black hole, if we're the holographic principle, then for time to pass, that means space-time needs to pass through us, which is why the universe is expanding. It's because space-time is blowing out of black holes. And the neutrino is essentially the flow of space, like you were talking about in my TOE, is like a marker.
Billions and trillions of them flowing through us at any given time. Because I've heard for years, and I'm like, that's very interesting. How does that?
Yeah. I mean, it just, and you see how it just all fits. Like it's just like it can't be any different than that. I don't see. I mean, it could, you know, but and remember, I didn't put this together. I didn't put this together like by making it up. I looked at every single thing that we could measure and like make sense, and I'm like, okay, this has to go here, and I think that's right, and whatever. But then it's just like, you know, and then once you figure out quantum gravity, and we can talk about that. Once you figure all that, then it's just like, boom, everything falls in place. You got it.
Well, that was one of the things, because I'm not necessarily sure if everything is a fact, but all I know is a lot of things you've been saying, I'm just like, my mind has been going in that direction. These are some of like the thoughts that I've been having, and it does sound a lot line up. And it's like you said, a lot of this stuff is established out there, and you're just kind of like taking these pieces, seeing how they might kind of fit together there. And that's what I find fascinating, just that passion and that energy to be able to focus on that. How the heck do we quantize gravity?
Yeah, well, okay, so I'll tell you. So if you consider you're on the surface of this black hole, right? Now, if you peel the surface of the black hole off and hang it like
just to go back a second, sorry, but when we're talking about like the holographic universe, we're basically making the link, because I don't think we had said this earlier, is that the interesting thing, at least according to I think I watched that same lecture a couple of times from Professor Leonard Susskind from Stanford, and I'm listening. He's talking about like apparently all the information from a black hole can be determined by its surface, and I found that fascinating right there. I'm like, why might that be a case? Even the Wolfram project, even Professor Wolfram at one point, he was asking Jonathan, it's like, wait, he was going to like say A of T or whatever, or A of N or whatever the power it was, would be like minus the one dimension and everything. He's like, why is that the case? Why doesn't it go up with the volume? And he was kind of explaining that, and I'm like, this is very interesting. That's also how I may or may not have been entangled and kind of did some of the things in the past couple of years with my life, which is also fascinating. But essentially, it sounds like a lot of the things from whether it's ADCFT, ADS-CFT, or the holographic, utilizing the holographic principle, if we're going to assume a holographic universe, perhaps a stereographic projection, if you would, basically all the information can be encoded at the boundary. And that's fascinating. So,
well, it's encoded on the surface, right?
It would not surprise me if we are within a black hole. And then that raises all other questions, but okay, let us establish, assuming that is true.
Where else is time blown out of? Like, no, I mean, the crazy thing is, and here's where it just will melt your brain. And this is when I was like, oh my God, man, so if our consciousness is on the surface of this black hole, right? The space-time blown out of it, right? Now, here's the thing. Do you know what Hawking radiation is? Hawking radiation is Stephen Hawking's baby. And it is information leaving the surface of the black hole as the black hole ages. And if our consciousness, and by the way, he proved it's heat leaving the black hole. There's information contained in heat. And that's why when I think when we die, Hawking radiation is our consciousness coming off of the surface of the black hole.
Whoa.
Carrying the information we've recorded in our memories and DNA, probably in fractal ascension, maybe to the next black hole. I'm a Christian, so heaven, whatever. But if in fact
higher dimensional plane per se,
well, I'm just saying that if it's true that we live in a holographic universe, and I didn't make that up. Stephen Hawking proved that information is carried away from a black hole.
Did he prove that, or it is heavily believed?
Well, no, it's consensus. It's consensus.
Okay.
It's
okay.
consensus.
Yeah, no, okay. No, I won't.
I didn't make it up. But I'm just like, fuck them. That's our.
That is one of the assumptions that we have. I've heard a lot of lectures about that, so no, I can go with that.
I have not heard of that. I saw that. I was like, holy fuck! And you know what that makes us? That makes us the mechanism, the universe's mechanism for the law of conservation of information. And we are recording information in our memories and in our DNA. And when we die, we leave the surface of the black hole with that information, which means our souls must be immortal. And that is a fact. Because there's a law of conservation of information. There's a law of conservation mass energy. And mass energy or energy can't be destroyed, and neither can information. So that means our souls must be immortal. And that's a fact.
Now, I cannot say what is true.
Sure. Well,
I tend to agree with that. I tend to agree with that. That's me personally. I tend to, and that's why I try to. It's like my personal beliefs, what I may best believe to be true, what I may feel in my gut, and what we may have the capacity to currently prove. There might be a difference there. I might be wrong. I just feel like we should be honest about that. And what you were kind of saying a little bit earlier about just in some of your videos, it's like, hey, listen, this is my perception. I'm just letting you know what's going on here, and just being honest about it. And what I did also like is in your video, you would also say, that is a fact, maybe, I think so. And like, you're like, I don't know, but like, this seems to make sense to me. And like that balance of, you said things very passionately based upon what you've seen, and you're also saying, hey, this is my best guess estimate. Whereas rather than just using like the over-the-top kayfabe, like this is what it is, it's like, well, is that what the truth is actually saying?
Sure.
Or are you just using a lot of thematics and cool hand-waving motions to try to prove your point? I do that a lot personally.
When you orbit in sonic gravity, you're viewing the universe through the eyes of a madman. So that's the whole caveat. And so you can, whatever I say, right? If I'm wrong, then you know it's wrong, So so there's some like, I mean, I do have a couple catchphrases. Like my catchphrases are maybe, probably, I'm pretty sure, and that is a fact. I mean, so like, I'm always saying stuff like that. That's kind of me.
Yeah, I mean, it put me in a super position, me, and I'm just like, I mean, like you said, I don't know if it's a fact, but I'm like, that's a lot where I've been learning a lot of stuff, and like, I'm going in that direction anyway. Let's hop on this river and see where it goes.
Yeah,
But,
I mean, like it's one of those things where, and like the stuff that I'm saying, like most of it is not stuff that I made up. Like most of it, it's essentially the stuff that I'm really, really sure is right. And then where there's intersection and I'm trying to get it to work, that's when that's when my brain started spinning.
You've got you found a number of very fascinating puzzle pieces. You're arranging them, and it sounds like the sonic gravity theory of everything is basically your attempt to basically take these pieces, find where they maybe don't quite line up, and what will we
Sure.
need to fill in the gaps to get these things to work together. But the reason why I love what you brought up here is because I started looking into this a little bit. It's like the UNRRA effect. Basically, the UNRRA temperature has the same form as the Hawking temperature. T of H is H of G, small g, over 2 pi ck sub b, with G denoting the surface gravity of a black hole, which was decided by Stephen Hawking in 1974 there. And those, basically, the UNRRA effect and the Hawking radiation have more or less the same form. And that is absolutely fascinating, because now you're talking about the proposed basically radiation emanating from a black hole versus the UNRRA effect, to the best of my knowledge, is essentially as long as one is under acceleration, as long as one is accelerating, it almost sounds like you're kind of outrunning part of the wave function of the power cosmic behind you, even a little bit. I'm like, only while you're accelerating though. And I'm like,
well, so now I haven't done a lot of.
No, I may have just slotted
like no, I haven't done a lot with the UNRRA radiation. But here's the thing: is that the gravity, right? Hawking radiation is heat coming off of a black hole, and Einstein's equivalence principle was that the force induced by acceleration, right? Force equals mass times acceleration, is indistinguishable from the force that you feel, the force of gravity that we feel from mass. And so that's what I suspect. That's what the whole UNRRA, the heat from UNRRA is like. It's probably just
well. The crazy thing is, it's based upon the observer. Apparently, like, one person is supposed to. No, it's nothing. Like, they're supposed to. If you were to accelerate that fast, basically, you need to go incredibly fast. But you would essentially disintegrate. But the other person would be detecting the heat, and like, it was really. I understand it? No, I don't. But I find it fascinating that they take a very similar form, and what that may. My madman conjecture is: do you necessarily need to be doing that on just like a large physical scale? What happens if one's mind is under acceleration? I don't know if that's free will or not. I have no idea. But
I don't know.
That's why I love talking about it.
Yeah. I mean, yeah, man. I don't know though. I haven't done, like, I haven't really thought about it. I haven't, probably because don't think that I've needed to, right? So like you'll run across like
path,
yeah, because like I said, like when it comes to anti-gravity, right? So I was like trying to figure out anti-gravity. So and I guess you want to get back to that. You was like,
oh yeah, absolutely. No, okay. that was a great thing about what I think Curt did, is I feel like he entangled a whole bunch of different folks, and I'm like, I hear a lot of folks, kind of like you were saying. It's kind of like in Professor Wolfram has said this before. It's like, in a lot of ways, it sounds like pretty much a lot of folks are right. Like, we all might kind of be right about, we're just coming at from different angles, different perspectives. Like, you were pursuing, how can the heck can I just get these crazy UAP stuff to actually work? How would this work? So you're using basic engineering style background. And that's the thing that I've noticed. A lot of folks with some engineering backgrounds have been saying some fascinating things. And I've been trying to look into it, learn a little bit of
like
stuff.
Pius?
Like,
yeah,
well, the thing is, there doesn't seem to be as much literature about that. I can find like a bajillion articles per se about string theory and stuff, and that's all well and good. And string theory showed that math can actually help model our world, and that is really neat. But at the same time, I'm like, the engineering perspective, they're focused on how do we achieve this goal, rather than exploring every single possible path with that. And I feel like it's going to be like the union between folks like that have been doing experiments, the experimentalists, and the theoreticians kind of coming together, taking these different parts of different models, different things that maybe they didn't know about, and just kind of linking them up. And I think that's how we truly level up as a species. Just
Yeah,
my
I mean,
opinion.
like when you look at, like, say you look at a wing, right? In order to make a plane fly, right? You camber a wing, right? So you just imagine, assuming no vacuum, right? So a little piece of air gets split here and it meets up at the end. Well, if you camber the wing so this is longer than the flat part along the bottom, then there's something called the ideal gas law. Pressure times volume equals the amount of gas times the constant times the temperature. So the bottom line is essentially you stretch out the same little piece of gas across the top and across the bottom. And that means that the stretched gas here is essentially less pressure. So there's less pressure on top, more pressure on the bottom, and that's lift.
Generates
Now,
lift.
yep. And so, and I'm talking about the cross section of a wing, right? So all you need is a camber on a wing and a shove, right? And you're going to get lift. Now, a scientist would get all wrapped around the axle about like, oh, well, let's do this math and figure it out. Like an engineer will go, all right, that's cool, but I see this is where my lift is, whatever, and then like build it and then go. Like we don't get all like constipated about, the little exactitudes and stuff when we're looking at building stuff. And so there are like some people will be like, oh, but did you calculate this and this and this, whatever? And I'm just like, well, I know enough differential calculus. I've got a bachelor's and a master's in structural engineering or civil engineering, and I'm a registered professional engineer in 2 states. I probably need to I think I've just let it expire because I'm not doing any engineering. But
I have expired licenses too. I could totally confirm that. But
but I'm not like all like
the back of the notebook calculations
about,
may be enough to actually achieve what we're trying to do at the moment. I feel you, man.
I'm more interested in can I do it than watching and seeing it work. And so, but essentially, so here's how anti-gravity works. So you take. So I said before, like just a little recap, right? Like I see them zipping around. Okay, that they're instantaneous velocity, which means doesn't matter if it's a drone, doesn't matter if it's a pilot, it has to be massless or it crushes itself under its own inertia. So I have to get rid of the Higgs field, or I have to get rid of mass. What gives matter mass? Well, Dr. O'Dowd on PBS Spacetime says the Higgs field gives matter mass, not just the Higgs boson, the weight of the Higgs, but whatever. But there's a function of the field that gives everything its mass. And so, and there's a vacuum expectation value of 246 gigaelectron volts. And so I'm like, okay, I got to get rid of that. So how do I essentially reduce the Higgs field in an area to the ground state? And so I'm like, well, okay, so how can I grab the Higgs field? How can I hold on to it? So I found another PBS Spacetime episode that says the Higgs field is pulling on the left-handed electron when it changes the hypercharge back and forth. So then I'm like, okay, so if that means Newton's third law, do you see what I'm doing? I'm like combining quantum mechanics and Newtonian mechanics here. So if the Higgs field is pulling on the left-handed electron, that means the left-handed electron is pushing on the Higgs field. So what I need to do is figure out how to grab me some left-handed electrons. And so I found some research from Professor Lawrence Eves from University of Nottingham, who's playing around with what they call graphene, which is essentially like a carbon sheet that's like one atom thick. And the carbon lattice, can you hear me?
No. It's essentially a lattice. I was just saying that while I was totally muted. Bring up a previous.
Yeah. So it's like a lattice of hexagons. And in his research, he says, well, when you pass a magnetic field through a hexagonal molecular structure, it teases out left and right-handed electrons, and those left-handed electrons sit in what they call cyclotronic orbits in that field. They just fucking sit and rotate. I'm like, that's what I fucking need to get rid of this Higgs field. So, and guess what? They say all these metamaterials and shit for all these UFOs, the skins of these UFOs, guess what it's made of? Magnesium, bismuth, and zinc. Guess what the molecular structure of magnesium, bismuth, and zinc is?
I'm going to assume it's hexagonal.
It's a hexagon too. It's a perfect hexagon.
That doesn't surprise me.
Yep,
Imagine my shock, everybody.
So now I know I need to pass a magnetic field through a hexagonal molecular structure to tease out my left-handed electrons, right? And then I realized that tension in a Higgs field, or like tension in anything in sort of sign convention, is negative. And so the one thing that departs from my perception of like fucking science and shit in the universe, my theory of everything does, is that the consensus physics community, the scientific community, thinks that the Higgs field is positive 246 gigaelectron volts. I think it's negative. And so, because gravity is negative energy density.
No, well, I mean,
gravity is negative energy density. And so the tension in that Higgs field is negative. In my theory of everything.
Wait. No. Let me steal your argument. Don't we actually know that is the case? Because wasn't it like Ben Franklin back in the day? He just took a wild guess and said, like, the electron, it's negative. But then we learned it is actually positive. So, I mean,
but nobody does.
It would have to.
It doesn't.
No, and we don't do it. No. But what I'm saying is, we assume it doesn't really matter. But I sit back and I'm like, does it not matter?
It matters for gravity because, well, here's the thing. It matters for my anti-gravity to work. That's the way it has to be. And it actually, I've lost a couple pounds, so I know it works. But it's tension, right? Which is what leashes that particle. It couldn't be, I mean, because what pushes particles away, right? It's weak nuclear force. Weak nuclear force opposes the gravity. And so gravity pulls mass together. Weak nuclear force tries to achieve entropy, which is kind of even shit out like a lot. So anyway, bottom line is the, so my departure from sort of consensus view is that it's negative. And so that's good for me, right? It's kind of self-licking ice cream cone because I don't know how to put in negative energy density. So, but what I can do is I create a magnetic field with what I call with what is called a Faraday disc. And a Faraday disc, you can look it up, is invented by a guy named Michael Faraday, right? And so it's a disc, and then it spins, and he puts a magnet on it. And what that magnet does is it shoves electrons to the center. Essentially, you can think of the magnet, sort of the U of the magnet, and the disc is spinning through. Well, that will shove electrons, using Ben Franklin's convention, right? Shoves electrons to the middle, which makes the middle more minus, which makes the edge more positive. There you go. That's right there. So you see that magnet, that sort of U, sort of scissor magnet. So that magnet is going to shove electrons to the middle. And then you take a wire and you connect the middle to the edge of the disc. See where that little tab is touching the edge?
Okay. See the so you got that there, and then we have the disc here. Go on.
So it's carrying current from the center of the disc through a wire to M so that you have a circuit. And whenever you have a circuit, you have an electromagnetic field. Anytime, and that essentially that's a battery, right? If it's more minus in the middle and more plus on the edge, then that's a battery. And if you connect a wire from the middle to where the M is there in your, on that diagram, you complete the circuit, electricity will flow, and it creates a magnetic field. But the delicious part about the Faraday disc is that the magnetic field blows through perpendicular to the surface of the disc. You shape the magnetic field with
the pointing vector, isn't it? It's
the
right hand rule. They say it's because like it flows in this charge, but it like spins or something in the other charge or something.
Well, like B is like the field, right? No, not that B. It's like a beta.
Oh, sorry. Yeah.
Anyway, but it's okay. It's okay. At the end of the day, what matters is this field is blowing through the surface of this disc, because that is the magnetic field that we're going to use, and we can shape it so we know it's going to blow through the surface of the disc. And then we put the hexagonal molecular structure. Can you like show my? I don't know. Let me see if you can see it. Can you show my? Can you just show my camera? See there. See up there. Now you see an oscilloscope on top. There's a scale on top of that filing cabinet behind me. Okay.
Okay.
So sitting on top of that scale is my anti-gravity generator, my VAG, my Voorhees anti-gravity engine. That's the 4th generation. And so it spins, and you can see the oscilloscope there. I use the oscilloscope. So anyway, so it spins this through this magnet. And then you see that silver sort of those sheets, those plates, those sheets. That's zinc.
Graphene.
That's zinc. No, that's zinc and graphene. I have like sheets of zinc sandwiched between zinc and graphene. And so it blows the magnetic field up through, right, that, and then it comes back around, and then it comes back through the other side. And so now, I have you got to have the field. If you look at the field geometry of like the one that was on Wikipedia, it looks like this. I mean, it's a mess. So I have like magnets evenly spaced around so that my field is nice and symmetric. And so then I have essentially two discs in there. Now,
are they rotating the same way or different ways?
Yeah, they're the same way. They're rotating the same way. But in one disc, I keep a constant field going. So it's like a polarizing field. So it just kind of keeps everything lined up. Yeah. And then the other disc, I attach to the oscilloscope, and the oscilloscope puts out a little. It's like a harmonic, like signal, right? And I can mess with the frequency and everything, and all that frequency means is you just make it do faster. Like you could do a kilohertz with 1,000 pumps a second, or you could do a megahertz
oscillation. You can adjust it. Yeah, Didn't you say you had it hooked up to like a stereo or something for power source?
Yeah, and so what I do is I take the oscilloscope signal and then I put it through a 3,500 watt car stereo just to jack up the wattage. But I don't think that's necessary anymore. But anyway, and so I put it through that car stereo and then essentially like jack it through the Faraday wheel. And so I'm actually putting out, I got a lot more juice going through there than just what the Faraday wheel and the magnets are creating. And so, I mean, yeah, just because I just was like,
I would be remiss. I don't want to cause a power outage or anything, but is there any way you could do a demonstration now, or does that require setup and everything like that?
Well, I'm gonna have
a video.
I will, I'll do a video, like I'll take it down and everything. When the wheel spins, like it gets damaged and stuff, and so I actually have to sort of reconstruct it a little bit.
Gotcha.
I have like
no worry. No, I wouldn't be doing my job if. Wait,
dude, I will.
That would be fantastic.
And I will totally do it. I will totally do it. But I will absolutely do that. And before I do it on anybody's show, I'll totally do it on yours, like no problem.
Cool.
But yeah, so
I do
this totally in my spare time. And the reason that I like totally got into it, and I was doing like 4, that's my 4th generation one. Like I have a bunch of them, and the reason I was like super hot and heavy trying to do it and test it and everything was because I patented it, and so I needed to be able to look that patent examiner in the eye and go, hey, this fucking works. I'm telling you it works. And so so I was like kind of hot and heavy, like my patent is still kind of working its way through the system and stuff. But
no, you filed paperwork. No, dude, you took the step and
I'm a patent.
You entered a contest and everything. And again, but
I didn't put any of this in the contest. None of this is in the contest.
Oh, that's
well, you
right.
You saw my video.
There's
nothing. There's nothing in that. I mean, I just thought
you mentioned it as kind of just in passing. Okay, yeah. No, that's I just find it interesting. It's like, okay, got an honorable mention and stuff, and I'm like, I did enjoy your video, and I think also one of my favorite videos was Surreal Physics. I may have fallen asleep to that, put it on one of my playlists just because of the music, the satire, going through the numbers. I'm glad she ended up being one of the winners there, but that's absolutely fascinating, and just knowing that there are other folks out there that are interested in this stuff. And I think shout out to Curt Jaimungal from the Theories of Everything channel, just letting folks know that these people do exist. There are other folks that are interested in the same thing there. And I think there's a lot of positivity. Personally, I spend a lot of my time just kind of in the culture war, just feel like banging my head against the wall and just talking to people that some of the same people that are on a live stream together that we arguing, butting heads. And I'm going to talk to them individually. And like I'm having a conversation and kind of going through at least maybe a Socratic method, if you will, just asking questions. And unfortunately, and this kind of got me a little sad, is I think a lot of time when you're dealing within the political sphere, I think too often it turns out I don't like this person. I'm going to justify reasons why. And I'm just like, all right, a lot of toxicity here. I'm like, let me go to science. Science is my safe space. And dude,
see all you beautiful
been
people,
one heck
you're
of a
all worried
ride.
about that. Yeah, no, not me. Like one thing I did notice, I thought Avi kind of got after Bernardo a little bit about, you know,
there was a disagreement, and personally, I feel like it was on a professional thing. It's like, this is what my career may or may not be. I'm not sure about many of the gentlemen there. I followed a little bit of Bernardo Castillo, I believe I butchered your name. I apologize, sir. But I'm just like, some folks feel like they need to push back, and I'm going to push back again with a little love and respect here. I think according to Professor O'Dowd's video, Matt O'Dowd from PBS Spacetime, I think the Higgs field, maybe it was another video, only accounts for 1% or 10% of the actual mass. I think the rest is like the energy in it of itself.
That's what I was talking about. That's what I was talking about. It's not the weight of the Higgs boson. It's the function of the field that gives everything its mass. You're exactly right.
Okay. Yeah. Okay.
Exactly
no,
right.
because I'm just like, okay, so that would I don't exactly know how it would work, but just based upon what you're saying there and other things like even.
Well, I mean, this is not an exact analogy, but think of it like jelly, right? Like a fucking swimming pool full of jelly. Now you can say the jelly weighs a certain amount, but the weight of the jelly is very different from the force it takes to move your ass through the jelly. You see what I mean? That's the difference.
So
I think that's
like
the way I think of it,
or something like that, because you could have something of a mass, water versus honey. Even if you would, it's like the viscosity is going to be a lot different there.
Yeah, same thing. I think that's the way I interpret it. And there's probably scientists who go, oh no, that's not right, or whatever. I don't care. But that's just the function of the field is not the weight of sort of the particle that represents, you know, that.
And this is what I love, is because this is a different perspective than what a lot of other people have been talking about. And it kind of goes down to, was it Sherlock Holmes or somebody had said, it's like, once I can end up finding out what I know, and you basically, I think, started off the whole podcast with this, or maybe it was before we had started. Okay, once you figure out what you know, if everything else is what you don't, if you eliminate all the other possibilities, why wouldn't you explore new ideas? As long as you're not hurting anybody or anything, it's like, explore the ideas, see where they go. It's a lot of times more wrong.
Yeah, man.
But when you happen across an idea and it starts lining up, is it not worthy of considering? What if this was correct?
Yeah.
Where may it lead us?
I mean, and here's the thing. Here's what happens is when you got it, right? And of course, I think I got it. I mean, it just, everything makes sense. Like, you can talk about quantum entanglement. You can talk about the Higgs field. You can talk about, you know, how does the dark matter mathematically arise from the existence of a holographic universe? Like, everything fits. It just all goes together. And like, people can say, oh, it's not right or whatever. I don't give a shit. Like, seriously, really, you get to the point where when it starts explaining everything, you're just like, you don't even care if somebody believes it. You just stop caring about convincing people. And it's just like, dude, that's cool. You don't believe it? That's fine. I don't care. Doesn't hurt my feelings. You know what I mean?
Just to support that a little bit is, don't get me wrong, I totally value a lot of the articles out there, because I'll go into some of these articles, especially if like I see a video from Brown University and they're talking about twisted bilayer graphene and achieving superconductivity. I didn't actually do the video because I ended up messing up the equation after the fact, but I put it into Wolfram Alpha at one point. I'm plotting out the vectors. I'm like, oh my God, it's like the Cooper pairs are literally swing dancers. And I had thought that idea at one point, and then I'm seeing it like literally happening, like they're spinning around in the particular way.
That's awesome, dude. I don't know anything of what you're talking about, though. I don't know what Wolfram Alpha
this might actually, it sounds like if you're utilizing kind of like even just a rudimentary lattice, if you have them lined up, and they were using hexagonal graphene right there, and I think the magic angle was just under 1.09 degrees or something like that, is where they would line it up. And then there was an additional form of like symmetry or an offset in symmetry where they were able to achieve that. And there's been a lot of studies. And like, don't get me wrong,
Achieve
I
what?
love those.
Achieve what?
Basically superconductivity at higher temperatures.
Okay.
As
And
well,
what
they were
was the
doing.
angle? The angle of what?
It was
Oh, the
basically
angle of
they had two
offset of the
layers, like
lattice.
one layer of one lattice,
Okay.
a second lattice, and rather than having them be right on top of each other, they very slightly twisted it, just
Yeah.
very slightly, and they were able to start observing these results, and that gives me a lot of hope because, especially, yes, we hit nav point alpha for we've achieved ignition per se. It's okay, ultimately like 1% of the energy, enough to maybe boil a cup of coffee or something like that. That's cool. We've hit nav point alpha. But I'm like, isn't the goal nav point zeta where we could literally, everybody could have a Mr. Fusion? And it's like, okay, if we can literally, as long as we have mass, if we can start to do hypothetical force, achieve what it sounds like we may be starting to unlock the potential of, if we can actually be like, okay, we don't necessarily need to worry about power. If we have the ability to transport that power without loss or absolute minimal loss, this is how I think like we kind of get over like a lot of our trivialities within humanity rather than arguing about things. It's like if you don't really need to worry about resources as long as you have mass, then we can do, I don't know, cool stuff like explore the cosmos, go where no person has gone before. I think that would be pretty fantastic.
Yeah, man.
Gives me a lot of hope. But we're coming up over an hour and a half. You want to actually?
Okay, sorry.
No, you want to actually. Did you finish with quantum gravity? I feel like we keep
No,
jumping around.
yeah. No, so at the end of the day, like you have, so then you have this magnetic field, right? That's blowing through your hexagonal molecular structure. You're teasing out your left-hand electrons, and they're sitting there in your field in these cyclotronic orbits, according to Dr. Lawrence Eves, right? So then, I have one Faraday disc that's putting out a constant field that's holding everything lined up. And the second one is hitting like, at a frequency, right? It's like, kind of, it's called a harmonic, right? Just this fancy word for just bumping. Like it's just off on, off on, off on, off on, off on.
Harmonics and so very important, I hear.
Yeah. So what we're trying to do is you can imagine there's essentially the left-handed electron that the Higgs field is holding on to. Now, are you familiar? You're like microwave oven, right? The way your microwave oven works is it bombards your food with microwaves. And the microwave will hit the molecule of your food. It's not ionizing radiation. It's not powerful enough to bust anything, but it hits it and it jiggles it. And when you make something jiggle, you're putting energy into it.
It's tuned to water. Isn't that like how it works? It like,
well, no, it just hits anything. It just bumps. It just hits anything, and it hits something, and it makes it jiggle, makes it shake. And so what I'm doing is I have these cyclotronic left-hand electrons that are hanging onto the Higgs field, and I'm going to bump them, just like you heat something in your microwave, and I'm going to shake them. Now, if I shake that left-handed electron, and the Higgs field's holding on to that left-handed electron, I'm putting energy into the electron, and that electron's putting energy into the Higgs field. So if the Higgs field is negative 246, and I can shake 246 gigaelectron volts into the Higgs field, I drop the Higgs field's energy inside that magnetic field. I drop it to the ground state. That means it can't leash the energy to our instance of time, and it fucking lets it go. Yeah. Well, no. So what happens is the Higgs field is gravity, time causes gravity, and we can talk about that. It's called time dilation. And so when you drop the Higgs field to the ground state in this sort of instance of Planck time, the Higgs field has to let it go. And so if it's negative 246 gigaelectron volts, and I put 246 gigaelectron volts into it, now it's got a zero field value, which means there's no gravity there. That's anti-gravity. It means zero gravity. So if there's no gravity, force equals mass times acceleration, right? So there's no acceleration due to gravity. So there's no mass. Force equals mass times acceleration. And if mass is zero, then there's no force there. So now it's just beep. It's right there. Now, there's a couple things that have to happen for that to, and and if you listen to PBS Spacetime, when something goes massless, that particle oscillates at the speed of light and its time stops, which means it's stuck in our time. And then now the mass has to go somewhere, right? So it has to go into the past. Now, and here's where the sonic gravity theory of everything gets rational, but a little bit woo. So if you think of, you're on the surface of the black hole, if you peel the surface of the black hole off, the surface of space-time off at any instant in time, that is the state of the energy in the universe at one instant in time.
A slice
And
of
you can
cheese,
sort of,
if you would.
yeah, like a slice of cheese, dude. Slice of cheese.
Like
Now,
cheese.
cheese is really good. So then if you can stack, and so it's like frames in a movie, right? It's like every instant in the movie throughout all of time. So you could chop all the frames in the movie out. You could peel the surface of the black hole off at every instant in time and stack it from the beginning of time all the way to the end of time. Now, the distance across those slices of cheese, right, becomes time-like, because it's an instant in time here. It's a little before that, little before that, little before that, little before that, little before.
We add up the slices, we can get a block.
Yeah, so you can think of that as sort of the bulk, right? And so if now the Higgs field is leashing the matter and energy, the mass, inside my field back there, in my if the Higgs field's leashing it to the slice of cheese, which is what I think it is. Remember, time is blowing through the surface of the black hole, right? And so if it's leashing the matter and energy to the surface, to our instant in time that's moving through time. And remember, this isn't me. This is exactly what Einstein and Rosenberg, ER, said wormholes were point-like that connect an exact state, like identical state of like an environment in time. It's point-like and it's across time. And so what that means is that on the surface of the black hole, in my theory of everything, or at least in what I call the quantum echo theory, when that electromagnetic field with those left-handed electrons excites the Higgs field, drops it to the ground state, the Higgs field has got to let go because it can't leash it anymore. Now, if it goes back to a slice of cheese, that slice of cheese can't accept that energy, right? Because it has to maintain conservation of mass energy, right? You couldn't drop it one slice of cheese back. It has to keep going. It has to keep going until the tension in the Higgs field, because I'm not breaking the Higgs field, I'm just reducing the energy to zero in this slice. So that means it has to go back into the past, and it's going to go exactly far back, right, as the tension in the Higgs field, which is negative energy density. We said, like, I'm assuming, right, at least in my theory of everything, the tension in the Higgs field is negative energy density. So I mean,
that would be negative to the mass energy of the Higgs boson. I mean, that would add up to zero. So at that point, it sounds like you've kind of decoupled.
Well, no, but remember, that's the Higgs boson.
Oh, okay, Higgs boson.
I don't want to go like totally into this, but I think the Higgs boson. So I think the Higgs field is that leash. And so when they pop a particle and go, oh, look, see this bounce? I don't think it's there. What they're seeing is energy. Okay. They're saying it's a particle. They say they think it's a particle and it decays. I think it's a leash. I think it's a rubber band that just snaps. And so I think that's space-time that's just jiggling like a drum. That's what I think that is. I don't think it's a particle. They can idealize it maybe mathematically as a particle, but I don't think it's, and this is just what would be consistent with, this would be a prediction I would be stuck with if I ever had to go discuss this or whatever. Yeah, right? Because I think only thing we can measure is space-time, right? That's the only thing our consciousness can interact with. That's the only thing we can measure. So when they see energy, I think when you pop something in a particle accelerator, and you essentially, there was something that was leashed to the Higgs field, and you just busted it, right? And so when that, like, whatever was pulling on the drum, essentially the surface of space-time, because it was leashed, when that particle explodes, Now all of a sudden you sort of have a rubber band. It's like somebody lets it go. It goes down. It's like a little, you see what I mean? It's like a barrel. And what they're measuring, I think, is essentially
It's like a break in tension.
yeah, it's the vibration
Something
in
like that.
space-time when something fucking lets go, when something disappears. It's not so I don't see it as a boson. And in order to have intellectual integrity and like say if it was a thesis defense, right? That's what I would have to say that energy is. I would have to say, no, it's not a Higgs boson. It's just the fabric of space-time that went doink. And when you blew that, whatever was leashed there, like if it was like a proton and we just like collided it or something and it popped, like if I was doing some kind of PhD thesis defense, I would have to say, no, it's not a Higgs boson. It's just a fucking. It's the surface of space-time that went boing when we popped.
You would need to use other terms because the way you've laid it out is you're like, the Higgs boson is essentially, and this is, and again, we're having, is this all real? I have no idea, but it's absolutely fascinating, and that's why I wanted to have you on. It's just because I feel like there's a lot of different connections between a lot of other people I've talked with publicly and behind the scenes, and this is how we actually learn. We go through conversations. Don't get me wrong, as great as reading different papers and everything are, and to just kind of go on, even Professor Wolfram and stuff, he has published papers and stuff like that, but a lot of his stuff now, he's like, I could go through this, I could like go through and argue with different folks. He's like, I'd rather just do my science and everything. I'll put it on my blog. I'll do a few live streams about different things, present my ideas, and if folks want to believe it, that's cool. If they don't want to believe it, that's cool. That people are entitled to their opinions. But ultimately, I mean, the truth is going to reveal itself down the line at some point or another. And if certain folks happen to get some things right there, I think we should give credit where credit is due. And I this is why I find this very fascinating. I have a lot of hope. I really feel like it has been said, rumor has it, that 2023 is the year to see. And I got really big hopes for that. And
so it goes back in time, right? And
when you say go back in time, what do you mean by that? Because
I mean legitly back in time,
like it from our reference frame, or like how?
No, well, because like say that we turn the field on, the mass inside the field goes to zero because the Higgs field can't hold on to it. It has to go back in the past.
Now you're talking
it has
like
to go back in the past.
Or
no, it goes back in time. Like remember, you chop the slices of the frames out.
Okay.
It goes back in time, legitly back in time.
So when you say back in time, you're talking like a reverse and entry, or
no? Well, so here's the thing: if the Higgs field is negative energy density, tension in the Higgs field is negative, right? And so the only place it can go is a place where the tension in the Higgs field, the negative energy density, balances the positive mass that we just ejected out of our slice of cheese, right? Because say you have a 100-pound ship, right, or whatever, that's inside your spaceship, 100 pounds inside this field. Well, that mass of 100 pounds, E equals mc squared, right? So mass 100 pounds times c squared, that's the amount of energy that you just ejected out of our slice of cheese. You see what I mean?
I mean, that sounds kind of like the equivalent principle or something.
Well, it's conservation of mass energy, right? So
okay.
So everything is energy, right? So mass, right? Like say you show a 100-pound thing, E equals mc squared, right? The energy of that mass is m, which is the mass, times c squared, the speed of light. That's the total energy in this mass. Now, if anti-gravity works, right? Like I'm suggesting it does, when you create a field and everything that was in that field just went massless, right? First of all, you have a mass hole, right, in our field, but that mass has to go somewhere. So it actually goes, and this is Einstein-Rosen. This is Einstein-Rosen bridges. This is wormholes through time, right? I didn't make this up. I did not make up wormholes through time. But Einstein-Rosen said that a wormhole is negative energy density. And so that's what you have if inside my field, which is a mass hole, everything just dropped to zero. The mass has to go into the past because positive mass can't go into the future, because it would be too much energy. So it goes into the past, and it goes exactly as far as the tension in the Higgs string all the way back balances it to zero.
Now,
And
personally, as a masshole myself, I totally want to say that's absolutely true because it sounds so fantastic. I don't know, but let me clarify. When you say
Sure.
it goes back in time, do you mean back in space time?
No, back in time. No, not space time. It's still in the same spot on the hologram, but it's orthogonally backwards in time. Just like we said, when we hang all those sheets. And that's really interesting because now space doesn't seem to be as fundamental as gravity. Because you would think that if something went back in time, if space was fundamental, right? Then that means if it went back in time, like Earth would be like, I don't know, fucking a million miles through space, a different direction, because we're going around the planet and we're spinning and we're going around the sun, and then the sun's going around the Milky Way, and the Milky Way is flying towards Andromeda. And so if we live in a 3D universe, none of this works. If we're living on the surface of a black hole, and all of the ontology that I've described, which I call the sonic gravity Rosetta Stone of the universe, that's the only way that I can see Einstein-Rosen bridges, wormholes through time working. So if we create this field, everything goes massless inside the field. The mass has to go into the past. It's got to go somewhere. It's still energy. You can't destroy it. But it goes as far back in time, and only as far back in time, as the tension in the Higgs string stretched across time dilation stretches to totally balance the energy of the mass we just lost. Now, if this is true, that's the recipe for Einstein-Rosen bridge wormholes. You need negative energy density, essentially zero mass, which is our quantum remainder, wrapped in negative energy density that's essentially created by the tension in the Higgs field when we just dropped our mass to zero and it went back into time, back in the past. And so at some slice of cheese in the past, you have 100 pounds of energy wrapped in exactly that amount of negative energy density, which is gravity. So it cancels. So that's good. Then we have our particles here in the future or in the present that are stuck in this time. This time's not moving. They're oscillating at the speed of light. And they're here too because they're timeless, which means they don't move in time. So now you have this point-like bridge. And so in our time, like say we turn on our field or whatever, our time is, we're still moving forward. We're still stuck in our time, but we're dragging like toilet paper to the bottom of our shoe, a quantum echo. I call it a quantum echo of our craft that's in the past. And so if quantum flight works like I think it does, you create the field, it goes massless, it ejects the mass into the past, it's wrapped in negative energy density. A lot of things. Now, this requires the following kinds of predictions. When we look and we see UFOs and UAPs zipping around massless, right? That means they have to be sitting inside of a wormhole. And they're in the exact same spot on the hologram. When we see them, if we see them, their quantum echo is in our time. They landed in our time. So that means we're looking at them in the future through a wormhole. Now, if that's true, you know how like it's nighttime, right? It's nighttime and you see like a big glowy ball. Well, that means you should be able to point a spectrometer at that big ball of light and it should read daylight. You should be able to see that's fucking daylight from the future. And that's why I funded my buddy, Gary Voorhees. And I said, I gave him like $500. He's building a truck. I said, I want a fucking spectrometer on that. Because the next time you see a UAV, I'm calling it, it's fucking daylight. And if you see one of them zipping around and it's red, guess what? It's fucking sunset on the other side. And when the scientists in like Ukraine, they're like, oh, we see these phantoms. Well, guess what? It fucking makes perfect sense. It's nighttime on the other side. The ones they're looking at were fucking nighttimes. And you know what?
Conspiracy analyst there. But
hey, you can call me whatever you want, but it's falsifiable, right? So you can call me fucking wrong. I don't give a shit. But you point a spectrometer at, my prediction must be that that's either daylight or it's nighttime, or it's sunset. That I'm stuck with that. If I'm gonna say I think that's what that is, then that's what the prediction is. And so, that makes that makes a lot of sense. But now here, think about this. So there's something called the ideal gas law, right? PV equals nRT. We talked about it. So now if you have all of that gravity, right? That gravity is going to create pressure. That pressure is going to create heat. And so now it makes perfect sense why everybody's like, oh, it's fucking controlled plasmas. No, it's just fucking hot, dude. It's friction. And so now there's like a Mexican Air Force thing where you can see like the there's this like little UFOs zipping around, whatever. You can see the field. I use it for podcast art for an episode I did like a year and a half ago. And you can see that field.
Like infrared or
no, you can see the lensing, the gravitational lensing around the craft, and its ass is like sticking out. And they were saying they were seeing shit melting off the back of it. That fucking makes perfect sense now. Because he's like, that guy's having a bad day. He's like, fuck, it's getting hot in here, man. And so now it makes a lot more sense why you see him dunking in the ocean all the time to cool that off.
Now, okay, so it sounds like the prediction for this would be basically if you see something in an area where it's basically nighttime, you're saying that we would basically observe what would essentially be daylight and or vice versa.
Well, I'm just saying on the other side of that wormhole, if there's a bunch of bright light coming out and it's nighttime where you are, if my theory of quantum gravity and my theory of everything and my quantum echo hypothesis and my anti-gravity generator, if it's on the right track and if it works, then it has to be daylight from the future. That's what it has to be. If it's right. If it's not right, fuck, man. Then no. It's
fascinating, regardless. There, and that's
so now. Now, when you see all these UFOs and everything zipping around in our military's training areas, well, it kind of makes a lot of sense, right? Because if anybody's going to have it on Earth, right, it's going to be the military. It's going to be the United States military, probably first. And so when we see these things zipping around in our military's training areas, well, now that kind of makes a lot of sense. And
I have sorry to cut you off, but I just have this random idea because at one point I remember a comic strip that I saw when I was a much younger memes, and it was something like where did all those $38,000 toilet seats go? Maybe it was from Independence Day. Actually, I sit back and like if somewhere on one of those UAPs or Tic Tacs it says "Made in the USA," part of me goes, all those $38,000 toilet seats were totally worth it. Now again, I would like to see no human being go without food and whatnot. If we had this technology, would be kind of cool. But then again, I'm also not at the point where it's like I also don't want to compromise the readiness of the United States Armed Forces.
Well, at the end of the day, like fan. I think the notion, the realization that this is what's going on. I think. I think it'll save us. I really do. Because once you realize that, fuck, man, there's so much more out there. Then who's really going to give a shit about trying to conquer other fucking countries? Like, who gives a fuck? Like, it's just stupid. It's a waste of fucking time.
My solution is if we get to the point where we don't need to be fighting over just a lot of basic necessities to just exist in life. If people still hate each other, heck, we could legalize dueling. That's I see. I just think truth, justice is the American way. I think honor would be a pretty good way to go, in my opinion. But I'm still trying to wrap my head around the whole going back in time per se. Now, it sounds like in my mind that I think Sir Roger Penrose had said at one point with that, like a photon doesn't experience time, or at least the way that we do. Is like you're talking? It sounds like we're going a state of change or a phase transition where something kind of remains in a particular way or form, and then relative to the rest of us, we're kind of progressing, but it's kind of stuck. Or am I just babbling a bunch of nonsense?
No. Okay, say that one more time. Let me make sure I'm catching what you're throwing.
Basically, what I'm hearing is it sounds like the way you achieve this, because like going back in time for me, I'm just like, I'm because I've
Yeah.
heard models where it's like you have like a localized time, you've had like super time and stuff. Like I can kind of conceptualize that because it's a much different scale of reference frame. But like if a photon per se doesn't experience time, it sounds like something electron negative 246 gig electron volts wiggling and jiggling within the Higgs field allows that to be in. It almost sounds like effectively like a superposition, if you would. Probably that's not the right word for it.
I don't know. I don't think it's wrong. I mean, here's the thing: is the field
Basically
is
we're
in
going
our
on, but
time right
something's
now.
staying the same.
The
It's like something
field is in our
wrong.
time.
Okay.
The field can't go out of time, right? Because the Higgs field is chargeless, doesn't have any charge, right? So anything that has a charge ain't going back in time, right? Only the bosons, only essentially, only
Something with no charge.
only the chargeless stuff goes back, right? So because the electromagnetic field is here, right? The electromagnetic field ain't going back. No. So you have it. So it's anchored here in our time, and it trails as far back as the tension in the Higgs field. The tension would need to cancel the energy that goes into the past. Now remember, the whole premise, right? And so if the premise ain't right, then it ain't right. But if you the premise is that all time exists in this holographic universe, in the bulk, it all exists at the same time. All time exists simultaneously, right? Okay. So this doesn't work if that's not true, right? So when you chop all, essentially, if you look at
you're anchoring it to basically like if we were in like a soup can, like assume like the soup is like the bulk per se within the can. It
yeah, like
sounds like you're connecting to
all
a label, if you would, that tells you like the soup in the can.
Well, no, you're okay. So I see what you're saying. No, so I guess the way I'm thinking of it is think of the slices of cheese, right? Yeah. So we have essentially the frame of so it's like a movie film, old school movie film, from the beginning of the movie, from the beginning of time to the end of time, right?
Right.
So we're going to chop all the frames in the movie out and stack them face to face from the beginning of time to the end of time.
Gotcha.
And so we're zipping through this movie, right, at the speed of light, right? And so wherever we are, so now just imagine we're still moving through space, at the speed of light or whatever, but just in the frame that we're in, whenever we're in it, the field is up, the mass hole is there, it's massless, and it's dragging back through time exactly as far back as it goes to cancel the mass, because it's the tension in the Higgs string, the negative energy density cancels the positive energy of the mass we just dropped out of our time. And it's now negative energy density, right? This is not me. I did not come up with Einstein-Rosen wormholes. What I'm saying is that if everything works in the sonic gravity theory of everything the way I think it does, I think that satisfies Einstein's and Rosen's recipe for a wormhole, for a point-like wormhole through time, linking two exact, what would they say? Two exact, essentially, exact environments, right? It's the exact same spot through time. So when you're in the past,
moving, is it because like we're moving, since we're, like you said, like we're on the Earth is going around the sun is going around about like 2/3 out the Milky Way, and the Milky Way is hurtling through the cosmos there.
So space space can't be fundamental. We have to be in a holographic universe for this to work. If it's really 3D universe and it's like space and shit, then this does not work.
We don't have the ability to basically latch on.
Well, it's just like the time. I mean, like it just like if you were in this, if space was fundamental, then this point where I'm in right now, like back in time, is probably in the vacuum of space somewhere between frickin' Alpha Centauri and some other place. You know what I mean? Like, because we're moving crazy through space. But if our universe is on the surface of this black hole, then we're stuck to this hologram, and then time is I don't want to say emergent, but essentially, if space-time's blown through black holes, which is why we experience time, then you can hang essentially the surface of the black hole like the bulk, right? Like a sheet, all the way from the beginning of time to the end of time. Well, now it works, and now it makes sense. And now wormholes that connect the exact same point in space through two different points in time, that's the Einstein-Rosen bridge. That's what it is. I'm not making that up. I'm just saying that if this works, if my sort of theory of quantum gravity and my Rosetta Stone of the universe and my theory of everything works, then that is a fact. That's what Einstein-Rosen said. It's a point like it's if they're right and I'm right, then my quantum echo hypothesis should be exactly like Einstein-Rosen's, ER, right? And that's what they said. They said it's a point like wormhole. And that's what it is. It's a point like wormhole connecting to exactly same spots on the surface of the hologram in time, in two different times. I mean, and that's not me. I didn't make that up. But
no. This is based upon it's based on. I've heard.
Yeah, and I built my whole theory of everything. I built my whole theory of everything based on all these smart people's stuff, and it accommodates all of their stuff because that's how I made it. I didn't think that up. I just put it together.
This is why this is one of the intros, because I'm still trying to wrap my head around like that whole time thing and just a lot of the other things you're talking about there. But the way you've been describing it has been to help clarify where, you know what, even if this instantiation, even if this isn't necessarily right, and you admit to that as well, the sheer fact that this is a different perspective, this is a different way of thinking about things. I mean, most everything in its current instantiation, and this is one of the things that Professor Brian Keating, you are a lucky son of a gun to be right across from Professor Keating the other night there.
Man,
dude, that was freaking awesome, man. Dude,
that's why I had to tell him. I had to say, hey, space-time blows out of black holes. I wanted him to hear it from me first. Oh, dude, man, before we end, I got to tell you this, because this is going to bake your noodle. Shoot. So if consciousness is on the surface of a black hole, if it is, right? And if space-time is blowing through the black hole, blowing out of black holes, and space-time uses the energy on the surface of the black hole, and this is talking, not me, because he said this is why Hawking radiation evaporates black holes. The energy has to come from the black hole itself. So if we're using the energy on the surface of the black holes to run our consciousness, right, to run our brains, to do our function of being the conservation of mass or of conservation of information on the hologram, if we use the energy on the surface of the hologram to run our consciousness, and time competes for the same energy to change the hologram, that means that when we run our brains, our consciousness slows the flow of time, because we're competing with time to use the energy on the surface of the black hole, because the only place it can come from, Hawking said, was from the surface of the black hole. And that's why we get tired, because when we're conscious and we're running our brains, the pressure of time trying to use that energy to blow out of the black hole and change the hologram makes us tired. And that's why when we get tired and we go unconscious, we release that energy, time moves faster while we sleep. Now, this is where it's really going to break your noodle. The human brain, 53 million neurons per gram of brain matter in the human brain. Guess how many? And so when we think of like what in our brain is going to take energy off the hologram, I'm going to say neurons, right? Neurons and synapses is what uses energy on the surface of the black hole. This is what's going to melt your brain. So the human brain, the neurons that do the synapses that take the energy, 53 million neurons per gram, right? Guess how many neurons per gram in a hummingbird's brain? 650 million.
I remember something about a hummingbird. Yeah.
So the hummingbird isn't fast because it has fast muscles. It's fast because it has slow time. because the conscious hummingbird's brain takes way more energy density off of the surface of the black hole than the human's brain does. So time doesn't have as much energy to move the hologram in the hummingbird's experience. And so that's why when a hummingbird is unconscious, when it's asleep, its heart beats 1 time a second. But when the hummingbird wakes up instantly, its heart starts beating 20 times a second. The hummingbird's consciousness slows the flow of its time, which makes it look super fucking fast to us. And if you look at ants, if you look at bumblebees, like 1 trillion neurons per gram in their brain. They beat their wings 600 times a second.
This would be a very interesting thing, and maybe
this
you've
is
done this,
falsifiable.
taking the points of different.
This is falsifiable.
I mean,
this
that almost sounds like
Here.
relativistic time dilation in a way.
It is. It's slowing the flow of your time. It does dilate. It totally dilates your time. The consciousness, it steals the energy that space-time needs to blow through the surface of the black hole to change the hologram. If that's true, and here's how you could prove it. And I told this to 2 different people at the University of Maryland. One of them fucking threw me out of his office, and the other guy was like, "That's an interesting notion." But if you took so this is totally falsifiable, right? Like you could totally prove me wrong. This is a consciousness experiment you could do. And the hummingbird, its heart beats, all that kind of stuff. So I think what slows the boundary of what slows time for the hummingbird is its heat. I think heat is important. And that's also what Hawking radiation is. So if you could prove me wrong, and I would have to say, yep, fuck, I'm totally wrong. You could prove me wrong if you took an analog clock and surgically implanted it in a hummingbird. If you did that and then had a control clock, somewhere else. If you did that and then at some point later took the clock out of the hummingbird's clock would have to be way faster than the control clock.
I'm not sure you'd ever get that past the board of animal ethics or anything that. But
you kidding me? I'll just tell them I work for Big Pharma. You want to know what they do to animals? There's plenty, and you could do this without hurting the bird. I'm certain. But you
could have a very tiny clock that you could. Because we already have trackers and stuff like that, and
you know what, we should already be able to falsify this, because people have pacemakers. There's all kinds of clocks in people. I will bet you it is common knowledge. Only they don't realize it. I bet you it is common knowledge that clocks tick slower inside people.
I think there are animals that actually have pacemakers, and not it.
I'll bet you that's true. I will bet you it's true. Dude, I don't know, man. Maybe I'm just going to surgically implant a clock on myself and see what happens. But I'm serious.
The memes of the Structure Channel does not provide medical advice.
Okay. Anyway,
what I'm sure any medication you use is prescribed by a doctor and obviously supplied by a multi-billion-dollar pharmaceutical company. Talk to your doctor.
Yeah, but it would have to be true. I mean, and I know it sounds bananas. It totally sounds crazy.
No, I like the bananas from Fermi Labs. Their videos there, just banana.
Yeah,
the crazy thing is, I need to talk to you more about this, just because I'm just starting. What you're just saying right now, it's getting my old noggin and jogging about other things. I feel like you're starting to connect different places in ways where I just had a thought and I didn't really see how it could be substantiated. This provides potential ways for things to be substantiated and potentially proven. But we've passed the 2-hour mark, Brad. Dude.
Oh yeah, man. Sorry.
Thank you so much for coming on here. This is totally fantastic. And dude, if this pans out, this is one of the reasons I like to talk to different folks. It's like, hey, if I happen to have one of the dudes that happens to solve basically a theory of everything, I think that's pretty damn neat. But we've got your link in the doobly-doo below and everything for anyone who wants to check out Brad and the Sonic Gravity podcast there. I'm going to have to go back myself and watch a couple episodes, but hey, that's all we got for now. Say bye to everybody, and hey,
thanks a lot. Hey, I appreciate your time, man. Happy New Year.
Oh, Peace out, everybody. We'll catch you all.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I like him.